So you start with a set of what we call vertices. For all practical purposes, you assume that they are numbers from 1 to n. Okay? They could be names of cities, they could be names of airports, currencies, or whatever. But for now, it's okay to assume that all of them are just integers. The more interesting part is another set, जिसको हम edges कहते हैं, and this set is a subset of pairs of vertices. Okay, this is what a graph means. So a graph G is defined to be a pair of vertices, which is just a set of numbers from 1 to n, and edges, which is pair of vertices, some pairs of vertices. Okay, so an example is due. So I guess I'm going to start with. So here is a graph on 3 vertices. Here is another graph on 3 vertices. Same set of vertices. And here is another graph on the same set of vertices. All right. So if we say that this graph is not equal to this graph, then we are talking about what we call is labeled graphs. Do you get a double L or a single L in labeled graphs? Single, double? Double? Okay, labeled graphs. All right, created 3 of them. Let me create one more. Oh, I created 1, 2, 3, 4, 5 of them. Does anyone know how many more can I create on the same set of vertices? So for all of these graphs, the set of vertices is just numbers 1, 2, and 3, right? How many graphs can I construct on set of 3 vertices?
8.
Why is that?
Because
Let me just make sure.
the vertex with 9 is 1 and the one without it is 0. So in absence it is 0.
Can you repeat one more time?
Yeah, so the absence of 9 is 0 and the presence is 1. So we get 8 combination.
What is 9?
Sorry?
Abscess of line is 0, and okay, so right, cool. He is correct, but here's the. So the maximum number of edges that you can have is, what is it? It depends on how you define edges. Okay, if I define my edges like this, how many edges can I have in a graph? Yes, I think you were right, whoever said whatever. Yeah. And factorial is not correct, sorry. V squared, V squared. The size of this thing squared. Okay, so that's the number of vertices that you, the number of edges that you can have. अब यहाँ पे जो मैंने examples draw की हैं, they are not these type of graphs. These are a different type of graphs which are called. So undirected graphs. Undirected graphs are graphs where edges are a subset of we choose to, or in other words, these are ordered pairs. Okay, which means the maximum number of edges you can have is size of v choose to, which is n choose to. Okay, and so the maximum number of graphs I can construct on 3 nodes, which are labeled and undirected is 2 raised to power n choose 2, okay, which is in this case correctly 8. Okay. All right, so that's that. I'm interested in something called connectivity or connected graphs. और ये define करने के लिए I will need to define something else, which is called walk. A walk is a sequence of vertices V1, V2, V3, Vk, where every consecutive pair is an edge. So that's a walk. So for example, if this is my graph, here is a walk. 1, 2, 1, 2. Okay, you can create infinitely many walks. I'm going to define something called a path as well. It's a walk with no repeated edges. So this creature is a walk, but this creature is not a path. Okay. Another example of a walk is 1, 2, 3. This thing is a path. This thing is not. All right. Cycle. It's a path that starts and ends at the same vertex. Okay, so far we are good. So a connected graph is a graph where every एक और चीज़ डिफाइन कर लेते हैं, that will help us इसको छोटा करने में. Reachable. So we say that Vi is reachable from Vj if there exists a walk from Vj to Vi. It's a bit hot in here. Okay, it's a connected graph is a graph where every pair of vertices are reachable from each other. A graph that is not connected is disconnected graph. So I'm talking about abhi tak mein I'm talking about undirected graphs. Any questions? Yeah.
What is the order or direction?
Order of direction is, this is how I find my errors when you ask for questions. This is unordered. Why didn't anyone talk about it? So order of direction is important at times, like in undirected graphs maybe. Okay, undirected graphs are the graphs where the order of pairs of vertices is not important. Walks are defined on both directed and undirected. Okay. You can define walks, paths, cycles, both in undirected and directed graphs. Undirected कर दिया तो मेरा ख्याल है directed graphs को भी define कर ही देते हैं क्योंकि it might be useful at some point. Directed graph is where E is what this is, right? It's a subset of V cross V. अब यहाँ पे caveats होती हैं. For example, one is loops allowed है या नहीं है. Generically, they are allowed. और क्या होता है? Right. So, a simple graph guys, keep it down. Why are the three of you? क्या up आ गया है? Up, Moise, right? Yeah, all three persons. Yeah, all three of you. बाकी अच्छा. Hadi, you are keeping time for me today, okay? Don't have a watch. Okay, a simple graph is a graph without loops. एक और चीज़ भी होती है loops and multiple edges. So graph में there is another abomination which is that you have two vertices, you put the same edge multiple times. Alright? ये आ जाए तो फिर we call this multiple edges. Usually हम allow नहीं करते, okay? So simple graph is a graph जिसमें this is not allowed. Okay? So this is V1 and this is a vertex V2 and you have two edges but both of them are V1, V2, V1, V2. Okay? So your edge set would look like this. V1, V2, V1, V2. अब यहाँ पे this is not a set anymore, right? Because you have the same element twice. और एक set में you can't have multiple elements. अब यहाँ पे this becomes a multi-set, if you want to call it. What else? Cool. Okay. So हमने connected graph define किया है. I hope this is clear. I'm gonna move it up and at some point erase it. So a disconnected graph is what you expect it to be. It's not connected. Gap shared. Didn't I ask you to come to the front in an earlier class? No? Answer. Do I have any of my TAs here? My TAs? You're here. You're इनका ID ले ले. उनका भी ले ले. Where's the third? The girl in red. I asked you to come upstairs. Don't leave your friends. Okay, disconnected graphs are the graphs which are not connected. So if you have a graph like this, और अभी मैंने example बनाई हुई थी कहाँ है? Over there. Okay, so the last two graphs are disconnected. Okay, so this is a disconnected graph, and this is a disconnected graph. So there is no walk from 1 to 3 here, and there's no walk from 2 to 3 here as well. Okay. Once you have a disconnected graph, another important concept comes into play, which is called connected components. और इससे पहले मैं एक और चीज़ डिफाइन करना चाहता हूँ, which is a subgraph. For a graph G, another graph H, V dash E dash is a subgraph what do you expect subgraph to be? You already know this, right? From discrete or data structures. It's a subgraph if three things happen. V dash must be a subset of V, E dash must be a subset of E, and E dash must also be subset of V dash cross V dash. Okay. It must be on the vertices जो आपने उठाई हैं. Okay. So for example, if I have this graph, तो फिर 1 to is a subgraph of 1 to 3. Okay? Questions? All right. So a connected component की हम बात करने जा रहे हैं. A connected component is maximally, I'm going to define this in a moment, connected ये हम define कर चुके हैं subgraph ये भी हम define कर चुके हैं. Okay? Maximally means कि if I add anything else, it will break the condition. Okay? So अब मैं कोई और vertex इसमें ऐड करूँगा तो फिर वो component connected नहीं रहेगा. Okay? So let me give you an example. So this is my graph 1 2 3 4 5 एक और vertex ऐड कर लेते हैं 6. Let's say कि आप ये कहते हैं कि 1 is my connected component. Then 1 is not a connected component because I can add 2 here and this would still remain a connected subgraph. Okay? But this is a connected component because now I cannot add any more vertices. Right? Similarly, this is a connected component because I cannot add 3, 4, 5 I'm pointing to is a connected component because I cannot add any more vertices. 6 is a connected component. So in this graph I have 3 connected components. Okay? You can name them C1 to C2 and C3. Questions? Yeah. Connected component is a subgraph. 6 is, the question is how is 6 a subgraph? So original जो मेरा graph था, if you're C was, I had 1, 2, let me write it down, 3, 4, 4, 5, and that's it, right? This was my original graph. Okay. Now I'm defining a subgraph. We call it H. अब इसका जो vertex set है, I'm putting 6 there. Okay. I have to define edge set, and that's how I define its edge set. Does it say that your connected component need to have an edge? So subgraph says, okay, so subgraph says that your vertex set should be from the original vertex set, and your edge set should be from the original edge set. And the third condition said that your edge set should be from the cross product of the vertices that you picked. Okay? I think it's fulfilling all three of them. So vertex set, which is 6, is a subset of original vertex set. Edge set, which is empty, is a subset of the any set, right? And it's also a subset of the cross product. All right, good. Cool. It's an interesting question to ask. If I give you a graph, so I talked about connected components, but usually you talk about connected component in terms of undirected graphs. Okay. We'll come to directed graphs at some point, but for now we're talking about undirected graphs. It's an interesting question to ask how many connected components your graphs have, and it's very easy to solve. You should be able to do it using what you learned in the tutorial or review session. Okay, so we just put it somewhere so that you have to go and do it at home. So write an algorithm to find number of connected components. Excuse me. Zainab is here. Zainab, can we put this on homework too? This problem. Find the number of connected components in an undirected graph. All right. I think a couple of more things before we, I don't know, actually do something. Weighted graphs. So another thing that you can do is you can define your graph as 3 things: vertices, edges, and weights, where weight is just a number that you put on an edge. Usually just a number, okay? So if I want to make this a weighted graph, I could say that this is 21, 0, negative 25, okay? And this becomes a weighted graph. Weighted graphs are important in what we are going to do. Cool. I think we are good. We have defined basics of graphs. All right. We are going to start a new graph algorithm paradigm that's called greedy. So let's see what greedy is. So a greedy algorithm what does it do? So it solves a problem by making a series of decisions. right? But you can say this about particularly, yeah, I think you can say this about any algorithm in general. But what's true about greedy algorithms specifically is that it makes each decision based on local information. What that means is that it does not look into the future. So a particular example of greedy algorithms is something called hill climbing. So you're on a curve and you're trying to find the maximum of that curve. Okay? So let's say you start somewhere here. Okay? At this point, you say that if I go to the left, I'm going to go down. By whatever I'm trying to do, I'm going to go down. But if I go to the right, I'm going to go up. Okay? So based on this local information, it makes sense to go to the right. Okay? So you take a step to the right, and at this point you make another local decision based on whatever information you have, and you go to the right. By taking these steps, you probably reach somewhere here, and you call this the optimal solution, because going to the left will also take you down, and going to the right will also take you down. Okay? But the problem with greedy algorithms is that they are not always correct, because it's possible that there is a hill somewhere here, which is higher than this one in altitude. Okay? So it would have possibly been a better idea to go to the left, to make a decision which looks locally suboptimal. All right? We'll see a few examples, but the main example that we are going to see for a greedy algorithms is the minimum spanning tree. All right, back to the slides now, I guess. Any questions? So I wanted to describe how I expect you guys to write an algorithm on the exam. And here's what I expect. I expect you to clearly write what's the input of your algorithm, what's the output. Remember, from your description of the input, it should be clear that what's the size of the input. Okay? That's going to dictate the runtime complexity that you are going to analyze. Okay? Then you write your algorithm in plain English or in list of points. Uske baad you give a proof or an argument about the correctness of your algorithm, and then you analyze your runtime. Okay? You do all this when I ask you to write an algorithm for a problem. Okay? I won't specifically ask you to, give me a proof of correctness or analyze the runtime of that algorithm and so on. Okay? I'm just going to ask you to write down an optimal algorithm for a problem. Are we good? Any questions? Okay, so greedy algorithms. A greedy algorithm is an algorithmic paradigm that builds on a solution piece by piece. You make decisions one after another, and each piece that you choose is based on locally optimal criteria. Okay? Whatever you do looks optimal locally at that given point. So yeah, important point is that you don't look into the future. Okay? You don't do any backtracking. It works at times, and at times it does not work. So if you compare it with divide and conquer also divides your problem into subproblems. That's where the resemblance ends. Backtracking what you do is you try all possibilities. Okay? You're not doing just locally optimal decision making. You're looking into the future, and you're also looking in the past. Okay? You're making a decision on global information. So at some point where you reach For example, if I were to reach at this hill, in backtracking, I would go back and try this path as well. So I'm possibly trying all possible paths. All right, it's useful because it's mostly simple, and it turns out to be efficient as well, runtime-wise. It's bad because at times greedy fails. It does not give you the optimal solution. All right, so for the problems where greedy does give you the correct answer, there is a typical way to show that it's working, and that's by showing something called greedy choice property. What you do is you show that the optimal solution contains greedy choice, okay? The greedy choice that you make locally at each step. You also show that it has optimal substructure, which is also part of divide and conquer. You show that at each point you are decreasing the problem, the size of the problem, okay? Otherwise your algorithm won't stop, okay? So that's kind of the proof strategy. We'll do examples. Here's an example which says that you are given an activities where an activity is an interval in time. Okay, so it's a pair of numbers, and you want to find out what's the maximum number of non-overlapping things that you can do. All right. So here's a greedy strategy. What it says is that select the activity with the earliest finish time that does not conflict with previously selected activities. This is greedy because what I'm doing is I don't care about any activities that I have to do in the future. I only care about this particular activity and any overlapping activity at this point. For example, if I am starting at 0, there are no activities, so I won't make any decisions. But when I am, for example, at 2.5 or something, at this point I care about the activities that are relevant at point 2.5. Okay? I don't care about any activities in the future. For some reason, this part of the screen is brighter than this one. Anyhow, so that's why it's a local decision. I don't look at activities, for example, A3, A4, A5. I only care about the activities which are locally important to me at this point. Okay? So what I do is, for example, I choose the activity which finishes first, and then make the next decision. Okay? So how do we prove that this is correct? We're going to use the same structure. The greedy algorithm selects activities by earliest finish time, produces optimal solution. Let A1 be the activity with earliest finish time. We show there exists an optimal solution containing A1. Remember, this was the first step of proving that greedy is correct. You show that the choice that greedy makes is part of an optimal solution. So let's say there is an optimal solution which selects optimal number of activities, B1, B2 up till Bk. If your activity is the first activity that you picked is part of the optimal solution, then you are done. Okay? So the problem is when it's not. So if B1 is the first activity in the optimal solution and it's not equal to A1, then I know that A1 must finish before B1. All right? Because I picked A1 by definition as an activity which finishes first, which means that A1 must finish, before B1, which means that if I replace B1 with A1, then it's not going to conflict any future activities. Okay? If B1 does not conflict any of the subsequent B activities, then A1 is not going to conflict with any of them either. Okay? Which means that I can replace B1 with A1. If I replace B1 with A1, I have replaced one activity in opt with one activity, which means the size of the opt, which was the number of activities, remains same. Now I have an optimal solution which contains greedy choice property. And that's it. That completes your proof. This is important that you understand this part because, sure. So F is the finish time and S, I think, is the start time of activity. So if B2 starts after B1, then it must start after A1 as well, because A1 by definition finishes first. Yeah.
B1 to Bk, that's an optimal solution, right?
That's an optimal solution.
So if we know that A1 finishes before B1,
Okay.
how is B1 to Bk our optimal solution?
So I don't know, right? So optimal solution is a solution of. So, right. So the thing is, you start with a problem, and then you hypothetically assume an optimal solution. Okay, that optimal solution may be different from what my greedy algorithm proposed. Okay, so my greedy algorithm proposed that I should pick A1, which finishes first. So there is a possibility that B1 is equal to A1, but there is also a possibility that B1 is not equal to A1. Can you think of a situation where B1 is not equal to A1?
So like the time, B1's time will be higher than A1.
Right, right. And even in that case, B1 is in the optimal solution and A1 is not. No? So think of a scenario where you can have multiple solutions which are all optimal. So for example, if I construct a problem which only has two activities, okay? So it has A1, which finishes first, and then it has a B1, which finishes later. Then A1 is an optimal solution, but B1 is also an optimal solution. So remember the problem. The problem is to find maximum number of non-overlapping activities. Okay? So the maximum number of non-overlapping activities is 1. You can pick A1 or you can pick B1.
So then what did we do?
So what we do is that we know that greedy is not going to pick B1. Greedy is going to pick A1, right? And we're going to show that regardless of what happens after B1, picking A1 instead of B1 will also give you an optimal solution. Okay? So greedy does not guarantee that it's going to give you. So if there is no unique optimal solution, then greedy cannot give you the optimal solution. It's going to give you an optimal solution. कोई एक optimal solution आपको देगा. And if you have an optimal solution in mind, what this proof suggests is that you can replace activities in this solution so that it becomes a greedy algorithm solution. Okay? So if you replace B1 with A1, you'll get a greedy algorithm solution. Yeah. So the question is about the difference between globally optimal and locally optimal solution. The opt is a globally optimal solution. What that means is that consider all possibilities, all possible solutions, and opt is the one that gives you the most optimal solution with respect to your criteria. Right? Your criteria is you want to select maximum number of activities. So opt gives you a global optimal. Okay? I don't know how you achieved it, but this is what it is. It's a global optimal. What this proof suggests is that greedy, which does local optimization, will also give you a solution which is equal to or at least as profitable as the global optimal solution. Okay, yeah. Let's converse. What's your objection about it?
Look at the non-time example. There is two depths, right?
Right.
There is locally optimal.
Yeah.
If greedy goes one way, it will find a locally optimal.
Yeah.
Globally optimal will be there.
Different, absolutely.
A1 will be that globally optimal depth,
Right.
Your A1 is not a globally optimal solution.
Right. So I think what you're doing is you're confusing. So this is not a proof that the greedy algorithm always works. Greedy algorithm doesn't always work. There are going to be cases, as we see here, where greedy is going to fail. But what this slide is doing is, did I break it? Yeah, I think I did. Okay, so what this slide is saying is that for this particular problem, the activity selection problem, if you do greedy, then you are going to get an optimal solution.
But in the case 2, you're saying that the optimal solution that you find is found using some strategy, and
Yeah.
the optimal solution using the greedy algorithm, that's not the same. So you're talking about the mountain one of these.
So what I'm saying is that, for example, for this problem, you can have multiple different optimal solutions. Okay? So, and greedy is, we're going to prove that greedy is going to give you one of them. Another way to, guys, keep it down, please. One way to think about it is that whatever solution you have in mind, and greedy give you a solution, I'm going to change my optimal solution so that it looks like the greedy solution. And both of them will have the same optimization criteria. So the criteria here to see that solution is optimal or not is the number of activities that you can choose, right? So if you have an optimal solution, which you got by doing brute force or whatever, if I look at the first, just a second, if you look at the first activity in that solution, is it the one that finishes first? If it is the one that finishes first, by induction, this solution is a greedy solution, right? But if it is not the activity which finishes first, what I can do is, this proof says, I can replace that first activity with an activity which finishes first. Now, the number of activities in the optimal solution is the same now, because I replaced one activity with another. But now, the first activity in this modified optimal solution is the one that finishes first.
But wouldn't that make the optimal solution not optimal?
It still has the same number of activities. Right? I did not change the number of activities in my optimal solution, which means that it's still an optimal solution. Right? That's the typical way to prove that greedy is giving you an optimal solution. Whenever it does, okay? Not always. Questions? On this side? All right. Let me try this thing one more time. No, it's dead. Okay, so shall we move on? But greedy doesn't always work. For example, if you look at this, you have a graph, a weighted graph on 3 vertices. And your goal is to find the longest path from a vertex A to vertex B. Right? What do I mean by longest path? What I mean is that the weight on the edges of the path, the sum of the weights on the edges, just give me a second, okay? Just let me finish the sentence. So the sum of the weights on the edges of the path should be maximum over all possible paths. Okay? So in this case, if you start at A, greedy is going to look at two possible ways to go from A to anywhere. One is of weight 5, another is of weight 4. Greedy is going to pick the one that looks optimal at that point, and it's going to pick 5. At that point, it's going to reach B, and it would declare that the longest path from A to B is of weight 5. But that's not the longest path from A to B, right? So in this case, the greedy fails. You can think about this while I ask you for a question. This slide? Definitely, definitely. So the question is, for this problem, can you have multiple optimal solutions? Definitely, you can have multiple optimal solutions. For example, एक simple सा case जो आप बना सकते हैं, जिसमें multiple solutions हो सकते हैं, वो ये है कि you have a million activities and all of them are overlapping. All of them are happening at the same time. Then all of them are individually the optimal solution. Right? The optimal solution will have only one activity, but you can pick any one of the million activities. Right? So you can have lots of optimal solutions. All right, so the longest path problem is a problem for which greedy does not give you an optimal solution. Are we in agreement? Yes? Yep. So in the worst case, yeah, in the worst case, you can construct a graph where greedy will fail. So we say that greedy will fail on a problem if there is a case or input where greedy will fail. Yes. Are we good? Cool. Let's move on. You're my timekeeper, right? What time is it? 51? Whoa. How much time do we need for the activity?
I think about 15 minutes.
Okay. Thanks. Cool. Okay, that leaves me less time. There's another problem called 0-1 or binary knapsack problem. You should look it up. We're going to discuss it at some point in future, maybe a couple of weeks down the line. Okay, I'm gonna rush through this because I think this is what we already discussed. The most important part of the proving that greedy works is the greedy choice property, and the second most important part is showing optimal substructure, which is saying that you reduce the problem size. Bolo, can you? Hello, Bolo? You have a question or an answer? Yeah. No, the guy sitting in front of you. क्या?
I was just asking कि,
मेरे से पूछो यार. This is what I'm here for.
so if, for example, if we get a question in the exam, do we have to follow these steps while answering them to get full marks, or can we just write a pseudocode for the answer?
So, okay, the question is if you end up getting a question like this on exam, what do you do? So, दो part होंगे उसके. You will have to write the algorithm. And the second part would be proving that this algorithm works, right? And proving that a greedy algorithm works is basically these steps. That you prove that it has greedy choice property. Whatever optimal solution you have, you can massage it so that it becomes a greedy solution. Okay? This is what we did for activity selection. All right. A list of problem where greedy works. Let me just make sure that it's, yeah, for all of them it works. So, for example, for binary knapsack and for longest path, it does not work. Minimum spanning tree is our problem. Historical context is, so this was happening in World War II, okay? And I think I have a picture. Guys, keep it down. I should not see anyone talking, guys. Keep it down. Keep it down. Keep it down. This group, do you need to be in this class? Do you have to be here? Okay. Okay. Doesn't look like it. Okay. It should look like that. Okay. Here's a graph, and here's a graph. It's a toy example, but the problem that was, I think, motivation behind minimum spanning tree was that you have a real network, and there is a cost to maintain every possible link. So this is possible links that are already there, and there is a weight which is the cost to maintain it, okay? Which is, I don't know, maybe to guard them, signal them, hardware costs, and whatever. And Since this is var, you don't want to maintain all of them. You want to reduce your cost, okay? And what you could do is you could leave some of the tracks unattended because they're being, for example, constantly bombarded. Your goal is to be able to transfer things from any place to any other place, okay? So every city should be connected to every other city according to our definition of connectivity. But the cost of maintenance of this network should be minimized. Okay? That's the minimum spanning tree problem. In a more modern context, you can look at the same graph and think of the weights as the cost to construct a fiber network. Okay? You want to connect every pair of, you want to make sure that every pair is reachable, and you want to reduce the number of, the amount of cost, well, the sum of weights on the edges that you are going to use. Okay? Is the problem clear? So here's one possible solution. I see a problem with this solution. Do you? Sorry?
These three are disconnected from Paris.
Yeah. Yeah, you cannot go from Paris to Lisbon, for example. So I think the correct solution would have this edge between Lisbon and Budapest. All right. So here's the formal definition. So you're given a graph. You're given weights on the edges. The weights are positive. Okay? We don't deal with negative weights in this graph. And your goal is to find the subset of edges which connect all vertices. This is called the spanning part. It should not have any cycles. This is not very relevant. अगर इसको allow भी कर दें तो you would still get a tree. And you want to minimize the sum of the weights on these edges that you choose. Okay, so for this graph, you have a bunch of edges. You want to pick a subset of edges, and you want to make sure that the subset of edges connect your graph, and the weight on this subset is the sum. The sum of the weights on these edges is minimum possible. Okay, that's the minimum spanning tree. I'm gonna just give you the brute force algorithm, which is that you try all possible subsets of edges and see whichever works. Okay, so for each one of them, you check if does this subset of edges connect all vertices, and then you compute its cost, and then you pick the subset that gives you the minimum possible cast. Okay, what's the runtime of this algorithm? N square to do what? So how long does it take to check connectivity? I give you a graph and I ask you the question, is this graph connected or not? How long does it take? N? Okay, and what is N? N is the number of vertices. Makes sense. So you, I think, studied it in the review. This, you can do it in one run of DFS, right? Awesome. So that you can do, and you have to do it for all subsets of edges. How many subsets of edges are there? Yeah. 2 to the power of the cardinality of edges. Okay, which could so in the worst case, this algorithm is going to take 2 raised to power the number of edges times some cost, right? Which is V plus E. So this is an exponential time algorithm. We'll see an algorithm which is called Kruskal, which you have already seen in the, I don't know, data structures. Okay, we'll analyze it. All right, this is the end. This is where we stop. This is the end of your syllabus for exam 1. Okay. Now we have a worksheet, and you have to find a pair.